year of experimental mathematics. I hope to see you all. I'm very happy to see new faces, and I really hope they do keep coming. But I have to tell you that you probably know, obviously, but just to make it explicit, in this seminar, there's absolutely no electronic devices, no texting. You have to pay. Everybody is welcome to leave the room, but if you're in the room, you're not texting and no other electronic devices. Today's speaker is our own Anthony, the future Dr. Z, who will speak about a very, very ancient problem, the isoperimetric problem that goes back to Queen Dido in Carthage, but in a very interesting twist on the isoperimetric problem.
Thanks. So hey everyone. So first I'm going to talk about the classical isochromatic problem. So that's, it goes like this. So suppose we define this energy of the set. So if we define E of omega to be the perimeter. So there's like technicalities here, but for now let's just say that omega is some set in the plane, so it's in R2. And so we're considering Lebesgue measurable sets, but I won't get too much into the details. So anyway, so we have defined the energy just to be the perimeter of a set. So the isoperimetric problem is this. So it says that we want to minimize E of omega while keeping the measure fixed. So we fix the measure of omega at some, say, m. So that might be odd since m is not usually used, but so I was working with sort of a physics guy, so this is like, like mass. So we use m is the fixed area of the set, and we want to minimize the energy, which is the perimeter. So most of you probably know the answer to this problem, right? So the answer is just take a ball, right? So if you look at all sufficiently nice sets of fixed area, the one with smallest perimeter is a ball. Okay?
Yeah. Does it make it connected?
Yeah, well, so we're looking at connected sets.
So the two-dimensional ball, also known as a disk.
Yeah.
Yeah.
Questions? Okay, so now what if we modify this? So what if we define this? So we have this new energy. We say E of omega equals, okay, so we have the perimeter like before, but we add this term, we add E of omega. So this is, sometimes we call this like the non-local energy or potential energy. So we define V of omega like this. So V omega is you integrate twice over the region omega. 1 over x minus y to the alpha. So what we're doing is so say this is omega. Right? So we have this region in the plane. And so we're picking x and y in omega. And we're evaluating 1 over the distance raised to some power. And then we're just doing that for x and y ranging in that region. So you can see that this decays with distance, right? So what I mean about that is if you look at a long set, like something like this, right? So if the points are in general more far apart, right? The integrand here is going to be smaller. Okay, and I should say, so we're assuming, so alpha is some parameter here, and the work we're doing is for alpha positive and small, so I want to say, alpha is greater than 0, but we looked into alpha less than 1, okay? So now we have the energy is the perimeter plus this non-local term, right? So
it's obvious that it converges?
So you're asking if there is a solution, you mean?
No, because you divide the zero, so it's obvious.
Okay, yeah, so it turns out that it does.
So it's an improper integral, but it's
Yeah.
conversion.
Okay, so the question is, why is this interesting? I mean, you could pick anything you want for the energy, right? So why would we add this term? So okay, so the perimeter. So we have the perimeter wants to pull it into like a tight ball, right? So, because if the V weren't there, the minimal energy configuration would be a ball or a disk. But now we have this non-local energy, right? That wants to push it apart to decrease the energy, right? So we have V. We say that V is repulsive. Okay? Because if it were just V and no P, then, well, to minimize the energy, you could just break into a bunch of balls and move them very far apart, right? So this wants to explode the mass, right? While this wants to pull it into a ball. So we have this sort of competition. We have this competition between V and P. So note that, so we have two parameters here, right? One is the area of this. So say this has area M. So we can vary that, and for each M we have a different problem. And also we can vary this alpha. Okay, another motivation for why this problem is interesting is note that this is the V of omega is a lot like the potential energy, right? So if alpha equals 1, that's like the Coulombic energy, right? So this has many applications in like physics, which I didn't look into, but it does. Okay, so first I want to show you that for certain masses, so we said that these two terms were competing. For certain masses, it turns out that this dominates, and you actually do split apart. So what we can do is this. So it turns out that if we look at a ball of radius r, we can actually explicitly compute the energy of that. So, well, the first term is just 2 pi r, right? Okay, and well, the second term, it should go roughly like r to the 4 minus alpha, right? Because you have the 2 area elements, and then you have the minus alpha. And it turns out that there's a constant here, c of alpha, which, so we use Maple, or I think we use Mathematica because the other guy did, but anyway, so we used some symbolic algebra symbolic computation to find V explicitly. So this is like, it involves like lots of gamma functions and stuff, but we have it explicit, kind of. So we have this. So now we can also do this. So
this is exact or symbolic?
yeah, this is exact. I mean, it's in terms of gamma functions, but it's exact. Yeah. So what we're doing is, so this is the energy of the ball of radius r, right? So now what if we break this into 2 pieces? So this has radius r. So if we break these into 2 pieces of mass, so I said m over 2, then the new radius is going to be r over the square root of 2. So now what happens if we compute the energy of this new set? So we're going to get 2 times E. So that equals 2 pi times r over the square root of 2 plus some constant times okay, and there should be, I'll just absorb the 2, so you get r to the, let's see, so 4 minus alpha over 2 to the 2 minus alpha over 2. Okay, so what we did is we were comparing this energy to the energy of this, right? So, okay, and notice that this is actually not exactly equal to the energy of, say, this set, right? Because can someone tell me what we're missing?
An interaction between two.
Yeah, there's an interaction energy, right? So if you have a point here and a point here, there's some interaction when you sum up.
Our ways.
Yeah, so the point is, since we're trying to minimize the energy, right? So if we can replace this with this and then move these, we can move these as far apart as we want. So if we're comparing the energy of these two, we can just assume that there's no interaction energy. Okay. So now you notice that. So what does this go like? This goes like r to the 4 minus alpha times c. And okay, I absorbed it too. Okay, and this goes like r to the 4 minus alpha times 2c. So it's going to be 2 to the minus 1 minus alpha over 2. Okay. So this is like for small alpha like a half, right? So it turns out that this has smaller energy for large values of r. So what that says is that for large areas, the answer to this problem can't be a ball, right? Because if it were a ball, then we could break it apart and decrease the energy. So you can actually, plug that into Maple, or even do it by hand and solve for exactly what r those two energies are equal. And so we get this. So we get that there exists some critical mass that we call MC1. It's going to depend on alpha, and it's such that this. So such that for the mass less than MC1, we have the solution to this problem can't be a ball. So so that already gives us, a little idea of what the solutions to this problem look like in parameter space. So the two parameters here again are they're alpha, right? The exponent in the integral of the energy, and m, which is just the area of the set. So we can, for each alpha and m, we have a different isoperimetric problem. So that tells us that there's some curve, and I think that there's some curve MC1, so that below this, above this, you can't have a ball. That's the solution to this problem. So, any questions on that?
Just one mistype there. 2 times square root of 2 in the formula for the parameter.
Okay.
Yeah. It should be bigger, definitely. So can we look at this such that we have like optimal radius? So if we don't talk about the mass, then for each e of r, we can actually find the radius for which the density will be optimal, which means that the system will tend to split into the parts corresponding to this radius. It's exactly the same when you see the showers, so you will get the radius of the balls of water in this sense.
Yeah, I didn't. So are you saying like, because we did do a thing where instead of splitting into 2 balls to give an upper bound on the energy, we split into say n balls and we optimize over n. Is that what you're talking about? Or something else?
Yeah, I mean the mass is not it's actually additive parameter. So what it tends to minimize the energy divided by the mass.
Okay.
So this.
Maybe you were actually going to do something like that. I'm not sure if it's what you're talking about. Let's go on. So instead of talking about the energy, we can also talk about the energy divided by the mass. Is that what you're talking about?
Yeah.
Yeah, so we call that the energy density.
So then for each alpha we have like optimal radius at which the energy density is minimized.
Yeah,
So it's-
something like that. I think I know what you mean. Okay, so let's do that. So what we want to do is, so if we pick any sufficiently nice test set, we have an upper bound on the energy, right? So we just picked a ball and we just picked two balls. So what if we do something else? So what if we do this? So this section of the paper, it's called upper bound on the minimum energy. Right, so say we have a set that does minimize the energy. We want to get an upper bound for what that energy is. So, okay, so now instead of working with E, we're going to work with rho. And we just define rho of some set omega to be E of omega and divide by the mass. So this is just that. Right, so minimizing E is the same as minimizing this rho, as long as M is fixed. So, so now what we're going to do is, okay, first let's find the energy density of just a single ball, right? So we can get a formula for that. Right, so it's just, so let's call that rho of R, right? Rho of R is the energy density of a ball of mass, or area pi r squared. So it's 2 pi r plus that constant r to the 4 minus alpha divided by pi r squared. Okay. So now again we can compute energy densities of, say, 2 balls. But why not? So what we can do is we can just do n balls. So if we do, so call this the energy density of n balls of mass m divided by n. Right? So this is going to be n times E of b r over square root of n. Right? So that's the energy density of each of the little balls. And then you divide by the total area, right? Which is going to be pi r squared. Okay, so the nice thing here is if you look, so, okay, this is just the energy of the ball radius r, pi r squared, right? So let's see, if you look at this, what happens if you take this and plug in r over the square root of n for r? You're going to get the energy of the ball of radius r over the square root of n, which is this. And you're going to get pi times r squared, and the n is going to come up, right? So it turns out that this is actually rho. So is everyone clear on that? We have the energy density of one ball, and we have the energy density of n balls of mass n over n. And it turns out that they're related like this. Okay, so we have this function, rho of r, which is just the energy of a ball radius r divided by its area. So we can, it involves like gamma functions and stuff, but we can just put that in maple and we get a plot that looks kind of like this. So I think it's convex, but I think its second derivative is positive, so it is convex, and it has a minimum here. Right, so this is rho of r. So okay, this is for alpha fixed, right? So for alpha fixed, we can vary the size of the ball, and we get different energy densities, right? So this is r. So it turns out that there's a certain value of r for which this rho is minimized. Okay, so just this curve alone, right, would give us an upper bound on the energy of the minimizing set, right? Because if you pick any test set, for example, a ball, it gives you an upper bound on the energy, right? Okay, so remember we just showed that rho n, right, is rho, but just stretched, right? Because you replace the r with r over the square root of n. So if this is rho, for example, this might be rho 2, right? And rho 3 is going to be stretched even more. So if we want a better bound, we can just minimize over all n, right? So there's this envelope and we take the minimum. Right? So we have all these convex functions, right? And they're all stretched versions of each other. So if you look at these intersection points, so I think we call this would be like rho C1, this would be rho C2. Right, so rho C1 is just the point where the energy density of one ball of mass m equals the energy density of two balls of mass m over 2. So we can just minimize this over all n and we get this spiky function. Okay? So and it turns out that, so using just like, some calculus and the fact that these have a positive second derivative, we showed that if you look at these intersections, they decrease. And so if you just look at the value at the first intersection, that's going to give you an upper bound on the minimal energy as long as r is sufficiently large, as long as you don't go here. So are there any questions on that part? Yeah.
Yeah. What is it true that for all values of parameters you have the minimized energy for n balls exactly when they are equal? Can it happen that it has less energy when you have n-1 of certain radius and 1 of different radius?
Oh yeah. So
because this might be the reason why you get this strange shape with rising the minimal energy.
Yeah, so I mean that would be harder to look at. I don't think we checked on that. So we didn't look at test sets of varying radii, but I'm not sure. I mean, because we were using this to actually prove non-existence in certain parameter regimes.
Oh.
So this bound worked for us. I don't know if there's a better bound. I'm not sure. Okay. So anyway, we have this bound. So say this value here is, well, actually, this should be like RC. Rho is on the y-axis. But anyway, so we have this rho C1, right? And so from this, we can get an upper bound on the minimal energy. It's going to be a linear bound. Right, so we have this. So the E of the minimizer is going to be less than or equal to what? So we just bounded the energy density. Now, so it's going to be maximum energy density times the what?
Times the mass.
Yeah, times the area. Right. So again, this is it's kind of messy, but it's explicit with Maple. We have that in terms of like gamma functions and stuff. So, and that's as long as R lies within a certain range, as long as it's sufficiently large. So we have this upper bound on. So if we have a minimizer, its energy has to be less than this. Okay, so now we can use that to actually find like the parameter regimes where we know that there is no solution to this problem. Okay, so there's some simple tools that we use a lot in our paper. So, okay, the first one is, well, first we need to observe that. So if there does exist a minimizer, must be connected. So does anyone see why you can't possibly have something that's in pieces as a minimizer to the energy?
Yeah. Just pull farther apart.
Yeah, so if this is the minimum energy, well, if you just pull it, you decrease the V. So if you do have a minimizer, it has to be connected. So for a connected set, we have this inequality. So we have that the perimeter is going to be greater than or equal to 4 pi, square root of 4 pi times the area. So this is the isoperimetric inequality. So pretty much just says that if you have a set, its perimeter has to be at least as large as the perimeter of a ball with the same area. And we also have a bounding the diameter that says, we write it that the perimeter is greater than or equal to twice the diameter. So the diameter is, so if you look at these 2 points in the set, right? So this just says that the diameter has to be, so the perimeter has to be at least this plus this, right? So that's intuitively clear. Okay, so now we can use these two. So we assume that a set is connected, and then we get that for certain parameter regimes, the energy is actually greater than this bound. So that's a contradiction, so that means there doesn't exist. Okay, so how we do this is, so let's assume that omega isn't a minimizer, and we have energy. So we have the upper bound, so now let's do a lower bound. So the energy is greater than or equal to, well, for the perimeter we have, no, actually, yeah, for the perimeter we can use the isoperimetric inequality. So it's going to be greater than or equal to square root of 4 pi m. Okay, and now, so how do we bound the other part? So remember, the other part was the integral of dx dy over x minus y to the alpha. Okay, so for this we just use a simple bound. So we can bound this from below, right? So the smallest this can possibly be is when x and y are the farthest apart, right? And so the farthest apart x and y can be, if they're in omega, it's just the diameter of omega, right? So we're going to get m squared from the area elements divided by d to the alpha, or diameter. Okay. Okay, so now, okay, so this diameter is still unknown, so what we do is we use the other inequality there. So if we put this inequality into here, we get 2 to the alpha over perimeter. Okay, now we still don't know the perimeter. So what we can do is, it seems odd, but what we can do is, so we know that the energy is the perimeter plus something positive, right? So that means the perimeter is bounded from above by the energy. So that means, yeah, so we have that oh wait, I'm sorry. So there should be, here we also have the upper bound of energy that we got before, right? So remember that was m times some constant. So now that gives us that the perimeter is going to be less than or equal to this, right? So in other words, so we can replace this with that, and this will still hold. Okay, any questions on this? So now we have both a lower and an upper bound for the energy of the minimizer. Okay, so now what we want to do is show that for m large enough, these are not compatible. So you look at this, right? So let's see what dominates. So it's going to be like m to the 2 minus alpha, right? So on this side, it's like m to the 2 minus alpha, but on this side, it's like m. Okay, so again, we're assuming alpha is small, so this is like m to the 2. So this goes faster than that side. So in other words, so for large m, we have this inequality can't hold. So what we have, so there exists another critical value of m, forgot, maybe m1, such that for m greater than m1, there doesn't exist an m1. So again, we can actually, using maple, explicitly find that. I mean, it might involve like some root function, like numerical root functions and stuff, but we can get it as close as we want. So we can find this curve, M1, that it goes, I think it diverges like that, such that we know that here, there's no solution to our problem.
Just out of curiosity, how long does it take Maple to do these calculations? Are they like this, or is they like,
they're instantaneous.
Okay.
I mean, it's not really hard what we're doing. It's mostly gamma functions and like f-solve, finding the root.
So you use floating point, so it's not completely rigorous.
Yeah, it's
In
not,
principle.
well, I mean, we start with rigorous things like the gamma function, and then we to graph it, we need to
Oh, yeah, I forgot.
use decimals.
We can probably use interval arithmetic if you want.
Yeah, so we did use interval arithmetic, and so there's actually a certain value of alpha for which, so this is alpha. So past this, we actually know that, so this is some critical value. So we know that for alpha is sufficiently small, the only answer to this problem is a ball. So to find this, we actually did, use interval arithmetic. Okay. So the next thing I want to do is, so we found when balls can't be minimizers, and we also found a region where there's no solution to the problem. So now we want to actually look into what the solutions look like. So it turns out that for alpha small enough, the solution to this is still the same as in the original problem. It's still a ball. So this is actually like probably the main part of the paper that we wrote.